A tiny, interesting device called an MCB protects you and your house from electrical mishaps. This breaker saves you from two situations: first, short circuit, and second, overload conditions. In a short circuit scenario, the MCB trips in less than 3 milliseconds and isolates the internal connections. Let's see how this smart device detects current chaos so quickly and precisely. A simple device called a fuse, which has a low melting point wire, was used for home protection in earlier days. In both the fault conditions mentioned previously, the current spikes up, resulting in overheating and fusing the wire or breaking the circuit. However, every time the fuse would blow, you had to manually replace it. Until you could do that, good luck with the blackout. This commonly occurring situation is why circuit breakers were invented. The circuit breaker is an automatic on-off mechanism that keeps one side of the wire moving and the other fixed. During an electric fault, if the circuit opens wide, we are done with the MCB design. After the fault ends, simply manually turn it on. Before getting more into the MCB design, a small note about the current direction. An MCB gets activated in less than 3 milliseconds, which is way lower than the half cycle time period of an alternating current. So it is okay to show the current flow in a single direction throughout the analysis. Now the question is, how does this system recognize the occurrence of an electric fault? The answer is that it has sensing elements which activates a triggering mechanism. Let's first see how we can design a super quick triggering mechanism which opens wide. A clever mechanism to achieve this objective is shown here. This mechanism has a lever to which a rectangular ring is connected, as shown. The rectangular ring is connected by 2 springs and a central lever. In this position, both the springs are in a neutral state. When the lever moves up, the bottom spring compresses and the top spring expands. The forces of both these springs are eventually transferred to the lever via the rectangular ring, and this force will be in the upward direction. As you can see, the rectangular ring is initially at a negative offset to the center of the lever. The torque produced by the force acting on the rectangular ring will be in the clockwise direction. If you release the lever in this position, this clockwise torque will bring the lever back to its initial position. However, if you push the lever farther up, do you notice anything peculiar about the offset distance? It suddenly becomes positive, which means that after a critical limit, the torque will act on it in a counterclockwise direction. When the MCB is on, this will be the position of the lever. The structure of the MCB will block the lever from rotating further counterclockwise. Now, if an external trigger turns the lever slightly, the torque on the lever suddenly becomes clockwise and the circuit opens wide quickly without the need of an external force. Here, as the operator pushes the lever down, you can see in ultra-slow motion how the mechanism operates in practice. After a small angle, the lever generates its own torque and then there is no need to apply external force. Now, the only question is, how can we generate this small input trigger or input motion when a fault occurs? The best answer is with an electromagnet. This coil produces magnetic fields proportional in nature to the current passing through them. As the current increases, the magnetic field becomes stronger. Throughout the video, note that in the case of a short circuit, the current rises up to 1,000 times in magnitude within milliseconds. This result generates a very strong magnetic field. An iron cylinder and pin is placed inside this electromagnet on a spring, slightly offset from its center. The strong magnetic field pulls the cylinder downward, thus pushing the pin. This tiny movement of the pin is the input trigger of the mechanism, and it leads to opening the circuit, as we discussed earlier. You might be wondering, in normal current flow, why isn't this cylinder attracted down? Well, the force in normal current flow is not high enough to overcome spring tension. whereas short circuit current can go up to 10 to 100 times the normal current. The force is quite high, so the circuit trips. The danger of fault is not over yet, folks. As soon as the contacts are opened, the current doesn't just stop flowing. The fault current is of large value and will lead to air discharge, or current will flow through the air. It is an amazing to watch and yet hazardous arc. To extinguish the arc, a component called an arc runner or arc chute is used. The arc chute is an arrangement of parallel plates arranged at small intervals. As the contacts separate, the heavy fault current flowing as an arc triggers a huge temperature rise that can cause damage. Therefore, this arc should be killed. Resistance increases with length and decreases with area. Here, we need increased resistance of the current which passes through air, which is why the distance between the contact points is kept high after the circuit opens. Since the air is hot, this arc will be pushed up. Later, the arc is divided into small chunks, thus reducing its area. With increased resistance, the arc dies away at current zero. Now let's see how the MCB prevents the second type of fault, an overload condition. An overload happens if you find yourself using a number of appliances at once. Since all the appliances in our houses are connected in parallel, such a scenario will lead to an increase in current. This is another dangerous scenario which we need to prevent. The current flow during a short circuit rises by 10 to 100 times the rated current, but in overload it only rises 2 to 5 times. You might think that use of a separate electromagnet with lesser operating rating may solve this issue, but it won't. Let's see why. The problem with this new coil for an overload condition is that it will get activated even if you simply start another electrical appliance. Fluorescent tubes, for example, carry an inrush current during startup that maintains for about 10 milliseconds and then goes back to normal. Therefore, using a lower-rated electromagnet will cause the breaker to trip unnecessarily when you start electrical appliances. A perfect choice to solve the overload condition is a bimetallic strip. This sensor is a bit slower and offsets inrush currents, as it stays around for only 10 milliseconds. However, it trips the MCB when the overload current maintains for 2 seconds or more. In a bimetallic strip, as the current rises, heat causes the strip to bend slowly. This occurrence pushes a C-shaped lever, and thus the main lever, down, and it thereby opens the contacts. The current value at which the bimetallic strip should operate can be varied with this screw, which is only adjusted by manufacturers. We hope you have now developed a good understanding of a miniature breaker. With this precisely designed device, you are safe from electrical disasters. Apart from MCB, we have other breaker types designed for different types of faults: RCD, ELCB, and MCCB. Don't forget to support us. Thank you.